All right, welcome back. So we're going to talk about infinite geometric series. So this starts off with the equality 1 plus x squared dot 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 all the way up to x to the n equals 1 minus x to the n plus 1 over 1 minus x. Now, here's a nice thing. If the absolute value of x is less than 1, then we can actually, in some sense, go out as far as we want, infinitely even, okay? So if we go out as far as we want, 1 plus x squared, and not actually even farther, okay? So that's what's going to happen to the left-hand side. It doesn't stop, okay? But what happens to the right-hand side? We get 1 over 1 minus x, because x to the n plus 1 goes to 0 in some sense if the absolute value of x is less than 1. Okay, so I'm going to do a couple of examples, and then we'll do a couple problems. Okay, so really they're the same thing, right? But let's just do a couple examples to sort of get a sense of this idea. So let's start with 1 plus 1/2 plus 1/4 plus 1/8. We keep on going. Okay, so we can think of that as 1 plus 1/2 plus 1/2 to the third. Well, I'm sorry, 1/2 squared plus 1/2 to the third, going on infinitely forever. Okay, 1/2 is certainly between -1 and 1, right? Okay, so it satisfies the condition. Okay, so this is going to equal 1 over 1 minus 1/2, which a little bit of algebraic manipulation tells us that's 2. Okay, now the reason I chose this one is this one actually has a nice graphical representation that we can use. Okay, so let's imagine we have a couple of boxes. I don't want it filled in. Take 2 of them. Okay, and we're going to represent the sum by filling in the boxes. Okay, so let's go. So 1, we're going to fill in this box. That's our 1. Okay, now 1/2. We're going to fill in half of this box. Okay, 1/4 is half of what's left. Okay, let's zoom in. 1/8 is half of 1/4. So that's what's left here. 1/16 is half of 1/8. Oh, this is beautiful. 1/32 is half of 1/16. I gotta go into a finer. 1/64 is half of 1/32. 1 over 128. Unfortunately, GoodNotes is not infinitesimally small, so I'm sort of stuck. So on and so forth. So you can see that this sum is going to end up equaling 2. We're just going to keep on going, okay? And I'll be honest, there's lots of paradoxes in math that come out of something like this. And it's not really a paradox in the construction, it's a paradox in our natural way of thinking, and that's really what what paradoxes really are. They're ways to show you that the way that you think about something is not completely consistent. Okay, so it's a way to refine your own way of thinking. That's one example I like. Let me do another example. Make this a little smaller. The other example I like is I like to show that 0.9 repeating actually genuinely equals 1. Okay? So now the way that I do that, the way that we do that is 0.9 repeating is actually equal to this first term represents 9/10. Plus, this next term represents 9/100. Plus, this term represents 9/1000. And you go on and so on and so forth. Factor out a 9. Okay, and we're going to get, let's factor out 9. Yeah, let's factor out a 9. Actually, 9/10. We factor out 9/10, what are we going to get? 1 plus 1/10 plus 1/100, and so on and so forth. So this is 9/10, 1 plus 1/10 plus 1/10 squared, so on and so forth. So this is, again, another infinite geometric series. Okay, we're going to go ahead. The R here is 1/10. So absolute value of R is certainly less than 1. So we can use our formula. So let me move this over. So this is going to equal 9/10, 1, sorry, no minus, it's infinite now, divided by 1 minus 1/10. Okay, 1 minus 1/10 is 9/10, so we get 1. Okay, so if you wanted to play around with this idea, what you might do on your own, similarly, is show that 0.3 repeating equals 1/3. That's another one that you could do. Okay. All right. We have a couple more, or just a couple more problems we'll get to in one more video, I think.